Hello, my name is Brody Kelso, and I'm a member of Group 8. Along with my partners Zane, Josh, Austin, and Derek, we will be showing you the importance of electrical resistivity and resistance. Many technological advances we take for granted today use electricity that may have to travel long distances or use a specific type of material. A couple of examples of this phenomenon could be the massive distances electricity must travel in the US power grid, and many extremely complicated computer circuits that must use treated materials like silicon. Even though it may seem like a complex topic, my friend Austin will guide you through the methods used to calculate electrical resistance.
E, the magnitude of the electric field, equals both rho times J, which is the resistivity of the material, times the current density, and V over L, which is the voltage divided by the length of the wire. So if we can set them equal to each other, and since J, the current density, is also equal to the I, current, divided by A, the cross-sectional area, we have V over L equals rho times I over A. We can multiply both sides by L to move the L to the right side of this equation, and divide by I, so we move the I to the left side of the equation. Now, because of Ohm's law, where we have V equals IR, R being the resistance, we can set the left side of the equation equal to R, giving us the equation for resistivity. R equals rho times L divided by A.
Here we have our resistance equation. Now this is resistivity times length divided by cross-sectional area. Our resistivity constant for this is for copper. It's 1.68 times 10 to the negative 8 ohms times meters. This also changes based on what type of material you're using. Length of wire, for the first one we did 1 foot, converted to meters is 0.3048 meters. Now the diameter of the wire was 0.06335 millimeters. You take half of that for your radius, square it times by pi, you get your area, which is 3.17 times 10 to the negative 9th meters squared. We plug all of this into, or using all of these values, we plug into our resistance equation. We get for 1 foot, we get 1.63 ohms. Then for 2 feet, we get 3.26 ohms. And for 3 feet, we get 4.89 ohms, which is about the sort of area we should be getting when we measure in our actual experiment.
For this experiment, we used one tape measure, a calculator, a barbecue lighter, some 42 AWG wire, 2 alligator clips, and one benchtop digital multimeter. So, we started by measuring the resistance in each of the alligator clips to account for any potential differences in our calculations. Then we broke off, or cut off, sections of wire in 1, 2, and 3 foot sections. So in order to ensure good connection with the multimeter, we used the barbecue lighter to burn the enamel off the ends of each wire. Then we connected the ends of the alligator clips to the ends of the 1 foot section of wire to measure its resistance, which we found to be about 1.93 ohms. Then we did the same for the 2 foot section of wire, which we found to be about 3.84 ohms. And for the 3 foot long section of wire, we found it to have a resistance of about 5.75 ohms.
So these are the measured values that we got when we conducted the experiment. And these are the values we got when we calculated before we conducted the experiment. As you can see, the values are slightly different, and we attributed that to the resistance in the alligator clips and also resistance and internal error within the multimeter.
Okay, so one product that this equation is useful for is a guitar pickup, which is essentially just thousands of wraps of, a really thin gauge wire. So how this applies is the resistance value of each one of these coils is a good determinant of how loud the pickup will be or how high its output will be. So in conclusion, the resistance is directly proportional to the length of a certain gauge of wire.